Okay, let's jump right into this explainer. If you've been tracking the intersections of arithmetic geometry and spectral projection theory, you already know just how dense and abstract these structures can get. But today, we're going to demystify it. We're going to explore exactly how the Adelic Langlands Program translates all that abstract math into a highly structured, step-by-step pipeline for proving the Hodge Conjecture. We're literally going to watch discrete data packets map directly onto continuous geometry.
We're going to treat this proof like an architectural blueprint. So we'll be tracking our data through 6 distinct stages. First, the Tate to Hodge bridge. Second, Satake parameter dequantization. Third, forcing the Archimedean shadow. Fourth, the non-Archimedean Fermat bridge. Fifth, stabilizing cycle-generating sheaves. And finally, the arithmetic index theorem.
So, the core thesis here is absolutely wild. If you look at the top grade representing discrete arithmetic data packets compiled across all finite primes, and then look at the continuous waveform below it, the framework makes a massive claim. It argues that continuous complex geometry, specifically rational Hodge classes, is really just the semi-classical shadow of these discrete invariants when mapped via Lagos field theory. It's a stunning geometric projection of pure arithmetic.
Let's start with stage 1, the Tate to Hodge bridge. Before we can even talk about the continuous complex Hodge structure, we have to lay down our arithmetic base, right? That's where the Tate conjecture comes in. Think of it as the arithmetic analog for Adelic homology over global fields. It essentially asserts that the subspace of vectors remaining invariant under the global Galois group identically matches the space of algebraic cycles. This gives us the exact, rock-solid foundation we need before we transition into continuous geometry.
And this brilliantly sets up our governing isomorphism. We've got the Galois invariant vectors on one side and the algebraic cycle space on the other. The Adelic Langlands program acts as the ultimate translation layer here, bridging this arithmetic structure directly to the continuous complex Hodge structure at the Archimedean place via the local Langlands correspondence.
Moving on to stage 2, Satake parameter dequantization. Now we need to isolate and dequantize our data stream. We track the dual coordinates through a really elegant 3-step logical flow. First up, we factor the Galois action to isolate the local Satake parameter matrices. Next, we take those rigid arithmetic eigenvalues and map them directly onto the spectral weights of a cuspidal automorphic representation. And third, we use those newly locked eigenvalues to trigger a unique arithmetic Ericalaw variety using the quantum J-flow stabilizer.
The absolute crux of this mechanism is the equation you see here. Alpha sub I, V equals Q sub V to the negative K. If a cohomology class is invariant, its local eigenvalues are rigidly, unconditionally forced to equal the weight of the Tate twist. That single arithmetic point is locked onto the grid, providing the exact stability required for our metric template.
All right, stage 3, forcing the Archimedean shadow. Let's push this forward to the infinite prime.
Notice how those asymmetric sine waves are structurally crossed out. That perfectly decodes the math, showing the global functional equation at work, where mu equals nu equals k. This explicitly proves that the global Adelic data stream can only radiate into the smooth k component. It physically, structurally forbids our continuous class from bleeding into asymmetric types, like k plus 1 or k minus 1.
And all of this culminates in a complete categorical cycle synthesis pipeline. We're finalizing the loop via the Grothendieck dictionary. The data starts at the discrete arithmetic core, flows seamlessly into the Adelic field stream, pushes forward into the Archimedean shadow, and realizes a smooth algebraic cycle. The quantum eigensheaves effectively compress right back into discrete indicator functions over those finite primes.
Next up, stage 4, the non-Archimedean Fermat bridge.
To see how this unified framework actually computes, we need a concrete testing ground. By placing these two equations side by side, it becomes super clear how the smooth projective Fermat hypersurface acts as our foundational non-Archimedean bridge for the canonical Hodge-Tate decomposition. The first equation gives us Fermat geometry over a local field. Then, Falting's p-adic Hodge theory tensor multiplies this by the completed algebraic closure, which triggers a split that acts as a discrete arithmetic scale factor.
Drilling down into this extraction equation, you can see how it precisely counts the active data channels operating at the Tate weight level. The absolute Galois group is acting semi-linearly here, but because it respects the Tate twists and the local conductor jump is 0, it ensures totally tame behavior. No irregular singularities, just a smoothly organized geometric data stream. As we track the filtration flow, you can literally see the algebraic variance getting stripped away, layer by nested layer. The continuous structure is being grouped into pristine, integer-quantized Tate blocks. And this is exactly what allows the discrete cyclotomic twist to map seamlessly to classical Hodge types when it gets pushed forward to the infinite prime.
Stage 5. Stabilizing cycle-generating sheaves.
Now we have to formally prove these sheaves aren't just analytical mirages. Enter the Bridgeland stability equation. This relies on the central charge function, z of e, to evaluate top arithmetic intersection numbers. By mapping objects to the complex plane, it acts as the algebraic avatar of the regularized parabolic J-functional. It's integrating the complexified metric template carrying those continuous B-field parameters.
Because we have a Galois-Tate invariant, this central charge is firmly locked to a quantized lattice. What that means is the sheaf is highly secured in a stable chamber, just as long as the phase inequalities are respected. In the semi-stable slice, that unique algebraic cycle is safely bound within its chamber.
But what happens if the continuous metric drifts across the stability manifold and actually breaches a wall? The phase inequality triggers severe turbulence. It completely fragments the main algebraic cycle, initiating quantum Harder-Nair-Siemann splitting. It breaks down into graded factors, reducible cycle sums. This goes to show that stability is the only thing holding the geometric shadow together.
And finally, stage 6, the Arithmetic Index Theorem.
For our grand finale, we need to count the exact dimensions of the cycle spaces generated by our arithmetically stabilized sheaves. We apply the arithmetic degree map here to measure those metric sizes. We use arithmetic K-theory for the Euler characteristic, and then apply the degree map to beautifully balance and weight the finite prime capacities against the smooth Archimedean volumes.
What is really fascinating here is the Gillet-Soulé theorem. Look at that subtraction term on the far right of the integral. That's the analytic torsion form. It proves that the size of the cycle space isn't just some arbitrary integer. That term is actively counting the vibration spectrum of the Langlands field theory, acting as a crucial regularizing density.
Which brings us to the final dimensional conservation loop. Arithmetic integration leads to spectral projection, down into Gillet-Soulé docking, and outputs the exact regularized metric dimension. It decisively proves that the exact dimensions of our stabilized geometric structures are fundamentally counted by the harmonic resonances of the Adelic wave equation as it flows toward equilibrium. I'll leave you with this one profound thought to ponder about the true underlying architecture of our universe. If the smooth geometric rules that govern our macroscopic world are mathematically proven to be exact projections of discrete prime number data packets, what else in our physical reality is just a shadow of arithmetic? Thanks for joining me on this explainer, and keep exploring.